Hello, hello. Start. So we are running our example code, and yesterday we were working on the PCB, the Encoder PCB, and we updated it. But after the stream, I just looked at it and thought to myself that I'm a lazy bastard, and that I did an awful job designing it, redesigning it, and I decided. I thought to myself that I need to redesign it again and do it better because currently it is not the best it can be, let's say. So let's do it. It may take a while, so today's stream may be mostly about electronic design. But if things go well, we will also implement break resistor control by the end of the stream, and maybe even some other features for our FOC implementation to get us very, very close to the production level code and hardware, I'd say. So let me open the project that we were fighting yesterday actively, and that crashed 3 times yesterday. Let's start working on it. So redesign will be very significant. It will be huge, actually. And huge how, you may ask, and huge in a way that we will need to introduce a separate TVS for power supply. Let me edit. To do introduce separate TVS for plus 3x3, I'd say. Then to do change current TVS connections to connect all 4 SPI pins to it, because yesterday we removed chip select and we used chip select channel for power, which is not right, which is not a good thing to do. If we are committing to using TVS, we need to commit fully. One moment, I will make myself a place to put my cup to without hitting the table like that. I would imagine it can be quite annoying for the viewers. So what else do we need to do? Give encoder full part number, to do move connector to the opposite side of the PCB, meaning left to right, and also move connector to the different layer from back to forward. Also update connector settings, library settings for it to be perceived as a THT component. I also think we need to add a test point to my libraries and update it to my standard. That's more like it. So this will be quite a list of things that I didn't like from yesterday, and there can actually be more, we will have to see. So let's start with going to the PCB and with actually just moving things around. So we need to switch layers. How do I actually switch layers in KiCad properly? No, that's not what I want. I actually want to remove layers completely. And then let's see these layers. Oh. What the hell is this? It's a fabrication layer. Oh no. Okay, we will fix it later. We will fix it later then. Let's see which side of the PCB it is on. It is on the side I want it to be on. Okay. So we will need to also move this around and move everything else around. So let's start doing this. Let's see how exactly we will do this. Oh, and we also will need to move the PCB out. So let's actually disable this, and I'd say this will be in our way quite a bit. We need to just remove all the lines for now, because all of them will be useless. Because what I want to do is I want to rotate this twice, so that we have our SPI lines on our right side, because I would like to route SPIs to not be under the IC, because this is a bad practice. And I don't want to populate bad practices on my streams. And what is the grid setting? It's fine. It's fine, it's fine. I'll allow it. Now we need to change all our connections, because what we will have is quite a problem. Now we will need to have power on the 7, which is actually very easy. So here will be our power. Okay, like this. Oh, brother. What the hell? W. Okay. Now we're talking. Like this. So what else? Please update. Perfect. So now we can just route it roughly this way. Which is not the way you do it, but we will fix it. We will fix it later. That's fine. Everything is fine. So now we need to make sure that we route our resistors correctly. This is the most important part, actually. This is the most important part, and I have quite a few traces I don't need. So please go away. What is the button for me to select the whole? Not is there a button? I'm not sure there is. But backspace works as well. So now let's make sure that it works as we expect it to work. Which is how exactly? So this will be the last pin. Alright, that looks good to me. So it will be roughly like this. I am back. The trip was nice. Last day we took a resort near a lake and view was nice. Ooh, that sounds very nice. And where were you going? Like, what was the place? Also, have you finished reading the document? Have you made any progress with embedded learning? Because you didn't provide feedback as you promised. Ay. Nah. So roughly like this. And let's say this will be moved like this to have space. We can technically move it much higher. I have no actual limitations on this. Hello. Please connect. Okay, so this will be here. How should I make it actually? Let's first align all the resistors to each other as they would need to go. So let's say like this. Okay. And also like that. Very good, very nice. And like this. And how will it go here? What are our options? What are our options? Okay. Connection order is almost right, but not quite. So this should connect to pin 5. Just here. I need to remove both of those. Has a network issue. Let me reconnect here. Sure. Take your time. Update. Okay, and this connection is incorrect. What is that? Awkward. This goes here, this goes here. So our misalign should be connected to 5. Oh, so this is wrong then. Then this is wrong because we need to do the misalign. Oh my god. Why do they use different hotkeys for the lines on PCB and schematic editor? That's annoying. So let's move our changes. Let's see. Now that makes sense. Perfect. So MOSI should go to 4. MOSI should go to 4. Like this. And I would imagine that SK should go here and should select. Oof. Okay. Okay. First, we actually need to redesign the connector. And actually, the way it is right now is absolutely fine. So we just need to connect this to chip select, as I would imagine. Okay. Not very straightforward, but we were solving harder issues. Oh my god. Like this. I would imagine this should be correct. Maybe not. So now, no, this is incorrect. Because chip select should be on 6. Chip select should be on 6. Okay. Kinda makes sense. Kinda makes sense. What the hell? Remove this temporarily. And this and that then. And let's just shuffle things around. I will move you or in my way. In this very moment. Holy cow. Okay. Let's check it. 6 and should be connected to the first pin. Oof, 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 oof. Like that. Looking good, looking nice. I would imagine this should be connected here. But I might as well be wrong. It happens quite a bit. Block. So this should be correct then. This should be then correct. Let's test. Update. It is correct. Very nice. Then ground, of course. And then we have our MOSI that should be connected to 3. Okay, perfect. Perfect. And chip select is supposed to have Apple up. Chip select is supposed to have a pull up. And also this pull up should be connected properly. So MOSI and MISO, and this should be connected to MISO like this. Let's check it. Is it correct? Okay, it is correct. And also 3 should be connected to 4. 3 should be connected to 4. And 5 should be connected to 2. And this symbol will be needed, but later. So let's see. It works fully properly now. It does. Okay, very nice. Very, very nice. So now let's align them. What are our properties? Let's say 91. 91. So we will use 91 here as well. It is already. And we can just touch. Previa. Okay, good now. Perfect. Welcome properly then. Okay. So how close is it? It is manageable. It is not manageable actually. I can actually put it even closer, like much closer. Which I will do. Oh, this is perfect. Okay. So what else? What is the location here? Like that, let's say. Let's see if it's still manageable. Still is. So tell me, Nilovu, how's your embedded learning going? And now we should probably group those. Let's move them as a unit. Will this work? Will this work? I'm not sure. We have space. I'm not entirely sure we have space. We kinda do. Kinda do have space. But it's kinda unpleasant the way it looks. I would imagine I can just rotate them 45 degrees. Is sound low? It is a question. My voice is low. I can speak louder or set it up louder. Give me feedback. If you think my voice is low, just tell me. Just tell me and I will fix it. Voice is low, okay. Voice is low, then let me see my filters. Okay, is it better? I'm talking to see if the filters are better now. Fine now, sure. Thank you. Thank you for the feedback. Appreciate it a lot. So how do I do this properly? How close is it? It is fine. Let's try rotating them. Just because we can. Tracks. Remove those. Everything. Connect. And how do I rotate? By an angle. No, but I want a specific angle. Can I do it? For a group? It seems like I can't. Now let me ungroup them and see if I can do it. See if I can do it. Actually, through properties. Okay, only through properties. That's annoying, but okay, sure. Works. Will this help us actually? Actually, thinking about it, I don't think it will help much, if at all. Yeah, it will only make things more awkward, so let's actually stick to this. Let's stick to this. Let's ungroup and move two of those one grid up. Now they are well aligned. Let's group them again. Two. Clean up. Connections. This will stay as R. This will connect directly. And now we can do it like this. And we can delete you. Nope. Not all the way here. And 3 volts go also directly. I have no idea why I did it terrible way. I did it initially because I had so much math like in the design, and we can do it so much cleaner. Like, I have no idea like what drugs I was on when I was doing the initial version of the design, but okay. So let's see. Like this. Looking good, looking nice. Like this. Oof. Actually, I don't like you. I actually don't like you. This is much better. Just don't make too many traces that I don't need, please, SkyCat. I beg you. Okay. So here. Let's do this part. Easy enough. Okay, very nice, very nice. Let's align them. Slightly. Don't ignore me, Nilubu. Tell me about your progress. Tell me about your studies. Okay, this looks nice. So what else do we have? We have 2 pull-ups. And let's see where they go. One goes here. That's annoying. Sure. And one goes here. That's very easy. That is actually very nice. You can simply do this. Okay. Unconnected. What the hell? Oh, this is unconnected, sure. And how will we work with this one? Of course, we need to do a via, and the easiest way to do a via here will be to do it over the calibration line, because calibration line is not important. And actually thinking about it, I might as well do calibration line on another layer just because calibration line is so unimportant. And the power line is much more important than calibration line. So let's do this. Orient. Move this and that. Can I even do it symmetrically? No, I shouldn't bother too much. Okay, this is fine. Now I need to add a component. I actually need to add a separate component before I finish it because it is not a finished design. So we need to add a separate TVS, which I found. Let me open the component name so that we can start adding this. So that we can start adding. And the component will be... Which one? This one. So this is a diode we will need to add. And let's see if KiCad libraries have it already available. It will be very useful, but if they don't, it's also fine. I can close this for now. Let me open our schematic symbol first. Let's see. Is it available? It is not. But there is a version that is available with different name, which is fine. We can just rename. Do I like how it looks? It looks acceptable. I would imagine. Also, there is polarity. There is a correct way to install it. I see. Okay. Sure. Let's then copy this. Copy. It will be in discrete because it is a discrete component. Paste symbol. Let's rename it. Hello. Hello. And this will be that. No. This will be this. But I also think I need more letters. What letters do I need? I don't know yet. So let's start solving questions one at a time. So this is not how I use it. Let's put it here. This pin should be 100, which is correct. This looks acceptable. Move it up. Move it to this side. Why do I have such a terrible snap? Okay. This should be left aligned. And snap like this. Okay. So how do I use it on my other components? Let's copy this for reference. Okay, it didn't copy. Let's just see it. First, the name, then description, then datasheet. First the name, then description, then datasheet. Okay. Perfect. Well, like that. And we also need to change the description. Oh, very interesting. This can be useful. Let me save it to my files because we will copy this and update from here. But as we saw yesterday, KiCad libraries, even though there are a lot of them, and they seem to do mostly nice work, not always provide the proper footprints and symbols. So that's why, that's one of the biggest reasons I support my own libraries. Because like, if there is an error, I would accept it only if it's my error, my personal error. Okay, ESD protection. Let's not clarify for what exactly. ESD protection and TVS. Sure, show pin number, show pin name, place pin. Okay, sure. Oh, I can. Oh, very interesting. Now I see. Let's actually update my test point then. So there is an option. Oh. Exclude from bill of materials can be done in the library. Very nice, very nice. Okay. So this is what we've added for now. One channel is the protection. This is not clear, it's correct, and datasheet is incorrect for sure. So let's update the datasheet to the Texas Instruments one. And what does Texas Instruments provide us? Is this the correct link? It is. So like that. And I would actually like this to be 0402 components, because I don't think I can solder a smaller one. It should be very small. So let's open the datasheet and actually see what I should select. What I should select, but no, this is not what I need. I need... I need a more general overview of the component, which should be like this. Perfect. So let's see the datasheet. Kids at home, always check the datasheet. Okay, so this is 0.02 and I need x1 son. Sons and daughters. Okay, x1 son should be here. Should be here. Yes. Okay, so we have our reference. So x1 son is what we need, which is correct. So this is confirmed. So what variant do we need then? Now that we confirmed that this is the case we would like to use, because it's just bigger for manual soldering. What these device options do we have available? We have 6 of them. Okay, so these are not what I need. And the difference here is I see no difference. Let's open DigiKey. digikey.com and let's actually start Googling. We should have D after this and P as well. And L. So all these numbers are needed. Letters rather. And we have 2 options, which are LT and LR. And datasheet says that one is, okay, they are the package differences. So R is not available, so we will use T, I would imagine. Damn, this is actually very expensive, holy cow. This is very expensive. Low. Now that's the price I would pay. But it is not a TI part. It is, oh, it is a copy of a TI part from China. And it's also an incorrect designed part. So this is a lie because the This is not how it's supposed to look. Oh, I was tricked. I was lied to. And they don't seem to have any original TI parts in stock. But also, if they were to have been in stock, they would have been even more expensive than on DigiKey, which is unfortunate. And this part is also very cheap. What is this? This is also in... No. This is correct. This is actually correct. Should I test it? Should I quite literally like buy it and test it? Because this is 50 times the price. 50 times smaller. Like, hello? I would actually note it for myself to test it because like 50 times smaller the price. Holy cow. This piles up very, very quickly. It's more than 50% lower the price actually. Incredible. Very interesting. PP. So R is the letter we would like to use, correct? No, we would not want to use any letter actually. Or yes, let's do without the last letter, because last letter is a package, and package, like, let the manufacturer, the PCB assembler decide the package themselves. They can do it, they can manage. I don't think I need to provide it fully. So this is decided then. So let's edit. And what should we edit? Hold on a second. Datasheet. Oh, yes, I remember. We should edit this. Okay. And this will be everything but the last letter. Like that. And now we also need to add 2 new fields. Would be a part number, which would be exactly the same always. And we also need to add a field for through-hole or SMD technology, which will be what exactly? This will be an SMD part, of course. Very easy. And also we need to do a manufacturer. And this field is also important. I'm just filling up the fields to fit the guidelines, instructions that I have from like one of my Chinese suppliers, which looks like this. And actually manufacturing. Oh, hello. What? Why is happening? Okay, so the manufacturer is important, as we saw like just yet, because we have a Chinese analog, which costs like 100 times less, but is an incorrect part completely. So we might as well want or need to specify manufacturer exactly for our supplier to not buy some crap. And for this part, it will be Texas Instruments. Okay, save. And this name should also be changed. Was? What is that? And why is it different? Let's copy. Oh, I see. So symbol name will be like this. Okay. Save. And we can put, I'd say, a generic manufacturer in case. Or should we? Like, thinking about it. So from this standpoint, the schematic file stores the information about manufacturing. So technically, if we talk about schematic files like 20 years ago, they didn't store any information about manufacturing. But should they? Because with this system, what we are trying to decide is whether to put last letter here or not, and whether to put manufacturer or not. Because if we do, to get new bill of materials, that will mean that in case we need to change only bill of materials, only the components, we will also need to generate new output files as we were making automation for yesterday. Which is an interesting question to have. Let me think about it. Do I have any objections to the system? The system seems unreasonable from the first glance, given that we need to change schematic when we only literally need to change bill of materials. But on the other hand, we want bill of materials to be fully generated. We don't want to touch it by hands at all. And from this standpoint, if our philosophy is that we don't want to touch bill of materials by hands, then to store information, we need to touch schematic. And that I like actually more, so yes, I decided. I made up my mind. This is what I would do. What is this? I have no idea. This is what, and this. Oh, these are new fields I've added. Okay, sure, makes sense. Makes sense. So, okay. And giving my philosophical description just now, what we will do is, like, thinking about it now, should I change it? I'm still pondering because I consider situations like, for example, you give a board to manufacturer and manufacturer says we don't have like the part X, so what part should we use instead of X? And you provide it. Or they switch it themselves. Like, how do you update your design files to actually make it work? And then also changelog will have to consider the bill of materials, which may be very annoying actually to have on the one hand. I think I'm thinking too much. Let's select this approach and let's stick with it for now. And then when I understand how the practical life works more clearly, I will go back and update. And for now, this works absolutely fine. And I need to change this name. No way you crashed. Fuck me. Okay, so KiCad crashed first time today. And I would imagine it would be first time of many. Oh, that was annoying. Okay, and you are not opening the project as well right away. Okay, I see you. I hope you saved what I've changed, because otherwise I will be pissed. You saved. Okay, KiCad, you can leave. You can leave because you saved my changes. But have you saved my changes to the symbol? Have you saved my changes to the symbol? Oh, you did. Okay. Okay, so everything is here. All the fields we need are populated. Part number may have to be populated by the on schematic itself, I would imagine. So this means that there are fields that will have to be populated on schematic. But whatever. Okay, this works. For now, definitely works. Okay, let's save it. And let's add the components to our schematic, which was TPD1. Okay. And this TPD1 should go with our power. We can just put it separately. It's not a big deal at all. I would imagine. And we can do it like this. Right? Okay. And here we put our 3 volts. Bloody hell, can you save my preferences, please? Okay. And ground in. Okay, so this is a protection for... No! It didn't save. Fuck me. No fucking way. It didn't save schematic. What? It didn't save anything in the schematic. It only saved PCB. Fucking. Oh my god. KiCad. I actually am very frustrated with KiCad. And this is version like 10.0.1. It should be like decently stable. And the crash again, it just broke my like everything. What the hell? And I'm looking at backups and I don't have a backup now. Like, what is the latest backup? What the hell? This is so annoying. That KiCad crashes so much. And not only that it crashes, it's like crashes and doesn't save anything. Okay, so this is the latest save. And schematic is not updated. Oh. Oof. Oof, 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 oof. Breathe in, breathe out. Breathe in, breathe out. Ooh. That was not a big deal, sure. Right? Okay. Okay. Like, I actually am very frustrated with KiCad. It should be much more stable. Like, the fact that it crashes and doesn't save shouldn't be like this. Yes, worse happened, but like, this is annoying. It's like 15 minutes of work out of like, for no reason at all. Okay. Okay, and I need to... Okay, sure. But my PCB is saved, so I will use my PCB as a reference on how should I reinstate everything. So let's use our PCB as a reference. I will open it on a separate screen because like it's not important that you see it, it's important that I see it, I would imagine. And this pull up goes to chip select, and chip select should be at line 6, which is here, which is incorrect. Incorrecto. So chip select should be here, and power should be on the 7th line, like this. So we should move all of this up, connect it here, and connect our first pull-up. Okay, so 5th pin will be clock here, and it doesn't need anything. So also our pin 6 should be connected to pin 10. Pin 6 should be connected to pin 10. And to do this correctly, oof, I will need to make some space, I would imagine. Move it slightly to the side, slightly more to the side. Okay. This makes sense. Use correct hotkey. Pretty please. Pretty please. Okay. So this is 6, then this is 5, which is correct. And what else do we have? What else do we have? What else do we have? Other pins. So 4 is ground, is correct. Then we need to delete this and move 2 of those up. Oh, very nice, very nice. Moshi right, and miso, and master in slave out should be connected to pull up. And now the last part of this process. Can I fit it here? No, it looks ugly. Let's not do this. We should actually move it here slightly. Not interfere with this. So I need to make slightly more space for everything else. and pin 4 will be connected where? To MOSI. So like that, and like this. Anything else? This is a new part. Let's save it, make sure it's saved. Any other changes we may require? Okay, this is not moved correctly. Nice. Move this a bit up. Okay. This is too much up for my liking. So this looks nice. Calibration test point we will update soon enough. And also we have updated the library file. Like, did it save the library file update? I'm not sure. I don't know. It should have. This we need to clean up, but this is fine. This is fine. That is fine. It should be all right. Let's save. Let's move to the PCB, which is already opened. Let's push our updates. Close. We have one more component, which is correct. Just a little bit tiny. But we also need to work on the footprint, so let's not integrate it into the design quite yet. And also, I would imagine this one is it correct? Interesting. So let's save. Let's go back to schematic and run the DRC check. ERC rather. So nothing is wrong particularly, which is very nice. So now let's go back to our libraries, which is here. So this component is updated. Let's see if our test point stayed updated. It did. Perfect. What else do we need? We need a footprint. So let's open our footprint manager editor, which is here. And let's see what we work with on the PCB itself as a base for our investigation. And this is called Texas TPY. Okay, let's copy the name because we will copy the footprint. Let's find it here. This is it. Copy footprint, and let's go to our discrete and paste it. And now let's start changing it to our style. And our style is 0.8, 0.8, 0.6, 0.6, and this should be layer 3. This reference should be layer 4. And it should be, this is fine. So this is done as a box, which is nice. And now let's open the datasheet and let's see the proper sizes and make sure that this part is within the specification that Texas Instruments want us to use. It should be lower. So length part pattern 0.5 and 0.3. Let's check it. All items paths, and the path is correctly sized. Perfect. Very nice. Not always the case. And the spacing between the paths should be 0.7, which means that they should be 0.35 from center, which is correct. Perfect. And they have a dot here, but given that this is technically a diode, not exactly, but still, I would imagine I would like to use my diode way of indicating this stuff, which is by using such a line. Nope. Copy and don't cut. So here, let's remove this. add this and update to size, update to fit. Roughly. This is close. Is it though? Nah, I don't think so. I actually don't think so. Okay, so that looks nice. Probably we can do even nicer. Even nicer. Okay, so this will be a diode. This is correct. What were we working with yesterday? Oh, I see. I see. Let me check the styling. This text should be 1. Okay. Let's go to our new component and make sure that this text is 1. Nope, not this text. This text is 1. 0.1, correct. Very nice, because this text is too big and it's too messy and it's not very important. And I hate when it's on the fabrication layer, because fabrication layer stores many more things as sizes, dimensions and stuff. So this is not the place to put this one. So center align probably is okay. Let me actually see my generic passives. How do I do this? I do a side align. Okay. Side alignment works for me. So let's do it to the side. Centered. Very, very nice. So let's save. At this point, do we need to do anything else? Let's see the 3D model if it is attached. It isn't. And it isn't because it doesn't seem to be able to find it. Interesting. Okay. Do they have anything Texas related? Texas. This is all? Okay. So it seems like the 3D model is lacking from the libraries, which is awkward. But fine. Should I edit? Not now, maybe a bit later. Actually, let's just go to the Texas Instruments website and just download it from there. I'm sure they have it. I'm more than sure that Texas Instruments has a 3D model available. Okay. Okay, it's available from Ultra Librarian, which is fine, good enough for us. And the version we would like to have is okay. I'm not a robot. I need a step 3D model. Sure. Okay. Very, very nice. Let's do what exactly? Let's copy it to our libraries, electronic libraries. To our here. I'm doing this off screen. One moment. Footprints, 3D models. And this will be street 1. So let's edit here. And this, it seems to be correct way to name the footprint, but it also names like this. And I don't see the naming of DPY at all in this document. DPY 00. Oh no, there is. Okay. So let's then keep it. But also, if it is a DPY, there should be a DPY in the libraries. This would be correct. So it will be not Texas, it will be just DPY to A, and no dimensions are needed because the name of the package is the dimension itself. And the footprint name should be exactly the same. Okay. State package. Sure, this can stay. Keywords. Very nice. Surface mount, correct. Nice, 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 nice. Okay, and let's attach our 3D model. That will now point to the location in all libraries, which is here. And here, and let's see if it works. Very nice. And let's save it. And now that we are here anyway, let's start updating all libraries to the new approach. So this will be 3. Oh my god, this will be 4. And this will be 3. Was. But don't use layer 9 anywhere. Oh my god. So are you happy? Are you happy? It's surface mount. Everything else looks correct. Let's keep going. Our LED. This will be layer 3. This will be layer 4. Okay, save. Transistor. Layer 3. Layer 4. And this package should be added yesterday. Layer 3. And layer 4. Okay, so this library is updated. Now that we are at it anyways, and that's not so many people are watching, I might as well go and update everything to be correctly used. So this is through whole part, the rest is correct. Save. No, don't tell me you crashed again. You didn't. Nice. Good boy. Good boy, KaiCad. Good job. Okay, let's keep going. 3 and 4. Save. Nope. We also need to update type to through hole. And now we can save here. So through hole. And my god. There is a correct order of operations to do this. And this is the order. Okay, so change layers first. Change layers first. And then change the description. Plus. What do I use layer 7 for? Holy cow. Brother. Okay, so change layer here. Layer 3, layer 4. Change description to through hole. Layer 3. Layer 4. Change description to through hole. Okay. 3, 4, Change description to through hole. A small song. Okay. So, and this is okay. This is our oscilloscope connection point. So layer 3, layer 4. Change the type to through hole. It is. Perfect. So connectors are done, discrete are done. And we have, we have quite a few to go. This is what you need junior engineers for. But I don't have any, so I'll do it myself. I will do it myself. That's correct. I don't like this song. Let's go next. Okay. We are roughly halfway there. We are roughly halfway to our target, which is kind of close. So bear with me. Surface mount. We are halfway there. Mount. Okay. Mount. I should probably just make a script to do this, but it's too late. I'm already halfway there, so I might as well finish by hand. But in the future, if a similar situation arises, I will be much better off using scripts to do this. This should be through whole components, correct? And also that the script, if it's implemented correctly, will make sure that there are no errors, meaning that I can just press an incorrect layer. But for now, we keep going. This is whole, correct. Oof, not you. Okay. I don't need you. I need 4. This is also through hole. And now that we are still here anyways, let's add a new test point that will fit our style. Now that we are working on this anyways, this is in the plans, so we might as well just do it right away. So make sure it is through hole. Okay. Save. And now let's go and search for test point. And what do we have here? Test part 1 millimeter. 1 millimeter should be all right. Let's copy. Actually, you know what? I cannot copy multiple. Annoying. Slightly annoying. Okay, so let's paste it. Let's delete this right away. And we also don't need such a huge keep out. Just test points, rather. Just test points. So this will be layer 3. It will be 0.6, 0.6, 0.1, 0.8, 0.8. Can also be automated with a script, I would imagine. Okay, and the reference should be much smaller, and it should be on the layer 4. Let's say 0.5, 0.5, 0.1. Right. And we should touch it to the center, to the very center. And center alignment for the reference is fine. Oh, it was actually a very easy update. We might as well just copy multiple because test points are test point, but one there naming convention does make sense. Now that no one is here anyways, let me just work on this. I will need this anyway later. What else do you have? Okay. Oh, I have a phone call. So I updated all the footprints while I was talking on my phone and also eating. And now we can update our newly added component, attach proper footprint from our libraries, which should be the Y, this one. And let's also make sure that it's datasheet. Pin 1 is supposed to be what? Exactly. IO and GND. Okay. So pin 1 is IO. Pin 2 is ground. Correct. Now we can go back to the design, use tools, update symbols from libraries, update, make sure that this has all the fields, which it does. Very nice. And now, what we want to see is a proper footprint. Very nice. Safe, of course, because KiCad loves to crash. Update, okay. Now we are updated. Oh no, why is it you though? Is it you? Is it considered NIC? Okay, if this is considered NIC, then I see why it makes sense to put a dot here. Okay, so if this is NIC, it should have a dot at first pin. If this is a diode, it should have. Okay, I think it is NIC after all, so let's actually change it. I would actually agree that this is NIC because it has 3 diodes inside. And 3 diodes inside is quite something, quite something. Quite a bit of something. So where was it? It was in this grid here. And let's remove these lines. And let's copy that. Yeah. Save. Nice. Tools. Update from library. Update. Very good. Very good. Exactly what we need. So now, do we also need to do anything here? Yes, of course. We need to switch the test point that we added to our own libraries. Where did we edit? Oh, generic testing. I see. 1 millimeter should be enough. Save, move, push, update. What is an error? Cannot update. Okay. Was. Oh, but I did a. Oh, this is from yesterday crash. Oof. Please save. Actually, let me push it at this stage, because if I am not pushing it, it will just crash again eventually, and I will lose my progress again eventually. So let me quickly push the git in the middle, updating the pushed. Now in the very worst case, we can at least come back to this exact situation, which is fine. Which is fine. So let's go here, let's update, should have 0 errors, perfect. And now this is perfect as well. Let's just 3D, it works nicely, and it's big enough to be usable. Let's change it to calibration and to knockout, because I really like how knockouts look in KiCad and that you can do them automatically. Very useful. And now we need to connect ground. Okay, let's see. I can entirely abandon having the ground here. Should I? I think I should. I see no good reason to have much of a ground there. But I see a good reason to have more ground in general, so let's make some more space for ground. Let's make some more space for ground. Okay. This looks nicely. And then it means that this will connect this way, which should be absolutely fine. Very nice. And let's move it here. Let's see if it looks fine on 3D model. It looks decent. It also looks like I have enough space to put my tweezers up there. U2 is a bit cut. U2 is slightly cut, but this is not a big problem. Program arrow. No text, please. Where is text? It's here. Okay. Let's see. This is good. And I don't need to cut anything. It all just works nicely. So it just works so nicely. I need to remove this and that. Maybe I will need those. Let me move them to the side for now. It's one of them. Plus. Okay. So now, oh no, we do need. Yes. We do need to do one via. We do need to do a single via. After all. So how do I align them nicely? 1, 2, 3, 4. 1, 2, 3, 4. I think they are very nicely aligned already. And I will put a 3-volt line here. Like that. And here I will actually start routing on that side. And I will just do a via here to finish the line. And this will be just somewhere just like this. Looks more than fine to me. The cut is not terrible, right? But the cut is in the feedback to power. And there is no ground for a while. Ah, whatever. It is manageable. Let's connect all of those. Because otherwise it wouldn't work correctly. This looks nice. Oof. 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 Brother. Thank you. Now That's much better. But also, I might as well put it higher, no? No, I need to make this loop short. I think this is most effective, the most productive way to do it. So let's save. And I think this is our update now. It actually didn't take that much time. I thought it would take longer. And we can even put some vias here. So let's see. Now we just need to stitch everything properly. But it's nice and dandy. Nice and dandy. Here, one there, one everywhere. You have a via, and you have a via. Do I even need vias there? I do, I can do. I better stitch this up everywhere. Vias are not very expensive, so we might as well use them. We might as well use a lot of them. Am I right or am I right? Okay. This looks fine. Everything is connected, touched here. This looks fine. This looks fine as well. And this via. Just for the sake of it. Put one here. One there. This. Here. 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 Roughly structured. Okay. That doesn't look half bad. Doesn't really look half bad. Maybe we can add one more here. And one more here. Just cause we can. So I think this is it. Let's run our DRC this time. We have 3 warnings. Okay. Oh yes, of course. I forgot to make sure the seal screen is all right. This is not all right. Of course it isn't. We can do it relatively nicely. That looks nice. And this should be placed in an attractive position. And U1 should be here. And I think these were all 3 of our errors. So let's rerun it. Bloody hell, don't tell me we'll crash again. Don't crash. Let's try it again. Still one warning. Footprint doesn't match. Why? Okay. Does it match now? Should I delete it and just do this? Because I can. This is not hard. But I just need to move it slightly And now let's see if we will have still the same error. Now we have more errors. Oh, I see, I see. That was funny. When you think you are done and you just have 4 more errors. Okay. Nope, I would like to keep you. Later, please. No bloody way, it didn't save. Oh my fucking god. Because I draw a line here. Oof, that's rough. That's really, really rough. Okay, now let's see the errors. What is that? Holy, what is happening? Rather, KiCad. KiCad! Behave! What? I better not continue. I'd better close the project, close everything, and reopen it, because if KiCad crashes, I will be pissed as hell. So let's do it. Here we are. What do you bloody mean this is? Oh, okay. Okay. It's fine, it's fine. So now that we are saved, probably, I actually think I should move the dimensions to the right side, left side rather. Because on the right we have connectors. This is much better. Oh, and also this seal screen should go. This seal screen should go as well. But first we need to make sure that we don't have any DRC errors. And my DRC window has absolutely gigantic size. What happens to you? Running, 0 errors, 0 warnings. Perfect, very nice. And let's fix the seal screen. Let's fix the seal screen. But I need to know what is where. So how do I do this? How do I do this? I only select text, then it will be easier. So ground now is here. So here is our calibration. How it is aligned by this, we can just rotate. And how will we put it? Let's put it on the white line. 3.3 volts is here. So the second one is MISO on the white line. Like this. Then it's MOSI. Okay. Then it's ground. Then it's ground, of course. Oh, oh. Uh-oh. We are saved. We are saved. No panic, no panic. Line. This. No. Yes. What? Are you correctly aligned? You are. Are you correctly aligned? Seems like you are. Let's see the 3D model. Boom. Decently looking. Decently looking. Yes. And readable. So the text is correctly oriented. What's about here? This text is incorrectly oriented. For sure. And this one as well. Oh, I actually don't like it because Fusion, for example, allows only 2 rotations per side, and KiCad allows 4, and like this is awful because I have all 4 orientations here, and we don't have any warnings for this. So let's go for this silk screen. Move it here. This is correct orientation. This is incorrect orientation, of course. I also need to mirror it then. And I cannot mirror it, so I need to change the alignment type. Oof. That's unpleasant, to say the least. That's rather unpleasant. Okay. It's rather unpleasant that I have to do this at all. Okay, we all have either looking up or looking to left. All our text is like this. Very nice. We don't need to rotate our head too much. Let's run DRC again. DRC is clear. We have some ignored tests, but it's fine. Is this first pin correct? Oh, it is. Okay. Okay. So how's the model looking? I'm not sure that I'm a big fan of this orientation. Let's change. Let's change it to be roughly on the circle. This way it makes more. It's much more pleasant visually. Much more pleasant visually. Okay. So I think this is the way to do it. This way it looks very good. Perfect. So let's save. Now let's fix this because we still have quite a few steps to go. We just finished the PCB. And let's actually push the PCB to Git. Just in case KK decides to crash us. Finished PCB update. Push origin. So let's clean this mess. This mess is very easy to clean. And also let's put values. I'd say that given that I would like to order them from China assembled, if possible, I would like to start with 10 ohms as a default value. I'm not sure if this is a correct approach, but we will see. Like that. This will stay like this. I'm sure that these values will have to change, but later. And that's mostly it. Now we need to do what? To update all the symbols. Oh, this will be quite an undertaking actually. But I'm not a lazy person, right? And you are not a lazy person, my dear viewer, right? Right? So let's just do it. And how do we do this? We open our KiCad. We go to our symbol editor. And we just start crunching everything. We need a way to do it nicely. We need to copy paste a lot. So let's prepare for the copy pasting fury. something I can put some text to. Very nice. And now let's open the components we just added, which is this one, and copy the names of all the fields, because we will need to add them to every single component. I'm sure it can be done by script, but we will need to populate most of them, so we might as well do it by hands. Okay. So what else do we need to change? Anything? We will need to change the encoder part number, because currently it is very lucky. So let's start. Let's start going one by one. So if is this part number full? Let's open our DigiKey and let's see how many different components we can find with this part number. It's only one, then we are golden. It's not only one, and the difference between them is that we will need to see the datasheet. So let's go check the packaging, where it will explain that the difference is shipping. So no, we technically see the only option. We don't need to provide anything after the T, but we better add the T. Also, let's check LCSC if they have analog, because we already figured out today that there are analogous components from other manufacturers, like this, for example, as well. And these are just cheaper versions of the same seemingly transistors. So we will need to add both manufacturer and everything else, actually. Manufacturer. Is the word manufacturer spelled wrong? Do I not know how to spell word manufacturer? I do. Okay, this is odd. So part number will be just this field. Nothing special here. Then through hole or SMD, it will be an SMD component. And this will be a manufacturer field. And the manufacturer will be on semi. Is this the correct way to spell the company name? It seems like so. Let me find their website. On semi. On semi. Yes, it is. Is the correct way. So let's move those down. Oof. Was. How do I even see the grid here? I don't see. Okay, good enough. Oh, that will take a while. That will bloody take a while. Okay, but we keep going. I will do the searches off screen on my second monitor, because this will just be much faster than if I will move my screen back and forth to show what exactly I'm searching. So this is an exact part number, which is perfect. Descriptions are correct, so we just need to add our fields, which will be populated with this. Then through hole or SMGs will be SMG, of course. Then manufacturer is Texas Instruments. Okay. And how do we align them? I'd say we should align them in the same order as we have part number. Yes, exactly like this. So, but also left aligned Oh, now I see that I will definitely need a hotkey to do this. Or otherwise I will just die. I will just die doing this. Otherwise I will just be dead. Okay, so let's actually add this hotkey. Hotkeys, justify, center, justify, left, justify. And what will the hotkey be? Let's say Control Q. It's already used. Okay. Control Z? No, of course it's used. Oh my god, am I a dumbass? Alt Q? Okay. So if it is centered. So it doesn't work. Fuck me. Okay. Preferences. Instead of Alt Q, let's call it Control A. It's already used. Control E. Okay. Control E. Just doesn't work. My god. Bloody hell. Whatever. Manual labor it is. So let's continue. I'd say. Okay. Like this. Let's add our fields. Part number will be this. It is an SMT part. And the manufacturer is Texas Instruments. Actually, can I align left? Okay, this is much better actually. So I can fix it faster. Okay. One library is done. Probably like 10 more to go. Let's see. Oh, more than 10. Oh, it's empty. Okay, and some of them are very empty. Okay. Well, it is unpleasant, but not awful. Test points don't need this. We have roughly like 30 components. And this is a generic component, so we just need to put fields. And we have no idea what they are, because they can be whatever, depending on the design. Which is very easy, and just make sure that everything is bloody left aligned, please. Okay, okay, -1. This is also a generic part. And for generic parts, we will only need to provide the fields themselves. Nope, I don't need another one. Very nice. This is a generic part. Oh, they are all generic parts. Ooh, very nice, very nice. So let's just do this. No. No, I didn't mean to do that. save. And keep going. No need for another one. Okay, this is quite... This is like fishing in video games. But compared to fishing in video games, this is a productive work that will be very useful in the future. It will be very, very useful in the future. Did I mess something up? No, I did not. Or did I? Right? I'm sure. I'm not sure entirely. Let's just keep going. We are halfway there, roughly. Yeah, actually, almost halfway there. But a few components will be much harder, so we are not halfway there. I'd say saying that we are halfway there is a lie. I definitely need to do it with a script. I believe it's so much easier with a script. But we are already so close. Might as well finish it manually. Okay. I'm in the zone. Oof, rough. Okay, -1. +1. Also a generic library. Generic library is very easy to work with. It's very, very easy to work with. -1. Oh, I decided to not even align them at that point. Oh, whatever. I'd say it's good enough for now. But I would imagine that it would be nicer if I were to pay attention to this more. But nah. Who knows, maybe I will wake up tomorrow and change my mind again on how this should be done, and then like you see it and like, expand. And now we're more to just update all of them. Just update all of them again, which would be unpleasant. Am I right or am I right? Okay, we are very close to finish. But here we may start to actually align things. And this will be harder because these are proper parts, and this is a terrible way to do it. This is a very bad way to do it. The SMD manufacturer is Texas Instruments, of course. Oof. Is this a full part number? Let me quickly check. It is a full part number. So this field will be a copy of this field. This will be SMD. Instruments. So have we edited everything we have? Let's align it. Very nice, very nice. So this, I would imagine, is a full part number as well. So part number. It's SMT, of course. Manufacturer is Texas Instruments. Yes, I do use a lot of Texas Instruments parts. How did you guess? How did you guess? Texas Instruments is a very nice company. They produce, and I would imagine that they are a very nice company not only because their parts are great, which they are, but also because they have incredible documentation, a lot of it, and also a lot of tutorials. Like just an incredible amount of tutorials to follow, which is amazing, which is absolutely just nice, nuts, good, perfect. And I'd say that this makes them even more impressive than the parts they have, which are also of a very high quality. This is just micro electro. Right, is this the official company name? Yes, it is. I will add it here because I will need it. Let's align everything. Manufacturer is last. Yeah. Was. No, this is correct. This is correct. Is this incorrect? And this is correct. Yeah, this looks odd. Oddly unproportional. Oddly unproportional. It's your spine if you're not following. Okay. SMD. They are all SMD. And the manufacturer is ST Microelectronics. Yep. Move all of here. This is the last. This is the first. Okay, very nice. Only slightly more than 10 to go. Yeah, this will definitely be not a full part name. And the full part name is... Actually, it's almost a full part name. Is the difference in the packaging? It doesn't seem to be, actually. We will need to open the datasheet to know. So let's see what they say in their packaging. In their packaging information, they say that, oh, they have a lot of variants. Just S, R, T, B, T, and R. Yes, and the difference is yes, tape and reel. Okay. So we can just simply add more letters without the last one. And this will be the most correct way to do this. Very nice, very nice. Let's keep going. It is an SMD part, of course. Manufacturer is Texas Instruments. Move it down. In the correct order, of course. Pyramid. Okay, why was I doing it like this before? I'm confused from myself. I'm confused. Maybe not really, but kinda. Not really, but kind of. But anyways, we keep going. Anyways. So what is this part? Is I would imagine it's also a Texas Instrument part, right? It is. Let's put it like this. This is SMD part. The manufacturer is Texas Instruments. Who would have thought? Who would have thought this part is in Texas Instruments part? Okay. Let's align. We are almost done and we will be able to update our PCB finally. And after that, generates manufacturing files, updates bill of materials to the final version, and after the bill of materials is updated, we are free to go and do some work on the software firmware. But for now, we need to continue. So this is also a bit awkward. We need to add this field as SMD, and manufacturer is Texas Instruments. Line them. Ooh, rough. Saved. Next, we have 10 more to go. We are almost there. Almost. Part number. This will be the beginning of the part number. It's an SMD part. That is manufactured by Texas Instruments. Right. Very nice. Okay. Put it here, put it there, put it here. A bit lower. Saved. One more. Go again. We go again. Just 10 minutes before greatness. This is also Texas Instruments part. It's also SMD. PI. Nope. This. Saved. Oof. We are almost there. Part number. My God, I should have copied it. Save. Field. Hold SMD parts. Manufactured by Texas Instruments. Okay. Okay, one more. We have 5, 7 left to go. Only 7 left. Do it. Just do it. Oh. Damn. Okay. Is this a full part number? Let's check the DigiKey. Is this a full part number? It is. So this is a full part number we can use here. It is an SMD component from Texas Instruments. Yes. Forgot Texas Instruments. Here and here. Very nice. 6 more. Only 6 more. Only 6 more. Is this a full part number? Let me check it. It is. So we can just copy it into the part number field. There is, of course, an SMD component from Texas Instruments. Of course, would have thought. Who would have thought? You up, this here, and this there. 5. No, 6 more to go. I lied. I'm a liar. I am a liar. Is this a full part number? It isn't. And the difference is that we have, okay, we have 2 versions. And they both have G and L and A. And after this is a difference. So the star is here. GL. Let me make sure that it works and that I didn't mess anything up. Yes, it works. And the manufacturer is Kemet. Kemet. It's an SMD part that is manufactured by Kemet. This is a capacitor. Kemet. Save. No, no. Don't say you crashed. No, it's crashed again. Third time today. Now let's see if everything's saved. I gladly pushed to the Git. So let's see now that we open project if it saved anything. So this is, okay, this is saved. The PCB that we updated today, it is saved. Okay, and let's see if our libraries are saved. But the fact that it's crashing, it's just keep crashing, it's annoying. And we were working with symbols. We were on our last 2 libraries. Yes, it's saved. Very, very, very nice. So let's align this to that. Nice, very perfect. We are very, very close to greatness. 5 more. Okay, this is oscillator, an oscillator, and there are hundreds of them. Holy cow. There are literal hundreds of them. And X is a terrible way. We need to use our star like this. Through hole and SMD. And the manufacturer for them is who? Epson. The manufacturer is Epson. Very nice. Very nice. Epson here. Save. 4 more to go. This is a current sense resistor. There are also quite a few of them, I would imagine. And the datasheet is missing, so we might as well add this when we are at it. Should we? Susumo. Company is Susumo. Add datasheet, sure. Build 6 is this one. There is, of course, an SMD part that's manufactured by a Japanese company. And the proper pronunciation, we skipped a letter. Susumu. No, not again. Rather, you just crashed. What the fuck? It's crashed again. Hello? Bloody hell, KiCad. That's annoying. So, we were working on the last 4 components. And this one from Susumu. Very nice. 3 more to go. This is our encoder, and I'm sure that the number and the name are completely incorrect. Not completely, but quite incorrect, because we need to specify an exact version. So let's do it. Oh, like this. Let's copy this here as well. Magnetic encoder correct. Part number. Manufacturer part number is this. It is of course an SMD part that is manufactured by a Chinese company called Magn Tech. But it on LCLC it is spelled in 2 words. What is the correct way? What is the correct way to spell it? Well, I'd say 2 words probably better. I'll use one. Magn Tech. And later, if it breaks, it breaks. So we are almost there. Save, and 2 temperature sensors from Texas Instruments, I would imagine. Let me Google. Dear Google, yes, they are from Texas Instruments. So part number will start from here. I also use different ways of identifying where I need to change the number, which is annoying. I annoy myself. Surface mount. Manufacturer is Texas Instruments. Okay. Save it. Let me hope through my libraries a bit later to see if I have the same delimiter everywhere. Okay. And the last part. Yoo-hoo! The last part. Very, very last part. Remove this. This here. Almost there. Almost done. Almost done. Manufacturer. STI. I is capital, of course. Let's go here. Save. Okay, perfect. Now let's go and see. This should change to star here. Save. Here, star, 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 star. So here I use all stars. Here I use Axis for whatever reason. Star. Star. Let me copy it. Copying will be easier. Star. And star. Nothing here. And the last one. Star and star. Nope, wrong letter. Star. Yes, we are done. Let me do a quick git commit push immediately. I updated quite a lot of things. Let me deselect everything. Let me do a quick push. So this one will be symbols. Edit proper bill of materials fields for all our components. Symbols. Push 1 and push 2 will be footprints and update all our footprints to a new style. Push. Now crushes are not dangerous for us anymore. And now we can go to our design. To our schematic. And let's press preferences. Nope. Tools. Update symbols. Update. And one error. You want Apple to the symbol not found. Of course, because I renamed it. So can I change symbol? And I will change it to sensors. Pass here. Change. Okay. Update. Okay, it's changed, but not fully. Value. Very nice. Now let's first let's do the ERC check. One warning. The current configuration does not include the footprint library. I see. Yes. I know I have an issue I need to fix in my symbols. Let's go to sensors here, and the link to the component is incorrect, of course, because I renamed the library. Very easy fix. Save. Okay, go to design, update again. Update, no errors. ERC check, run. No errors. Very good. Go to the PCB, update everything. No errors. Everything should look fine. And let's do the DRC. No errors. We are done. Woohoo! And now we need to generate the manufacturing files, just like to make sure that everything looks in order. Nothing looks particularly broken or particularly out of place. And now let's do our magic that we prepared yesterday. So the magic will give us all our manufacturing files in a single click. Actually, I lied. I know that I need to update dates as well, but almost in a single click. So let me go to my project. Outputs. So we expect to see new outputs here, but first, let's make sure that our dates are updated. This is today, correct? Nope, correctly. And this is today as well. Very nice. And now we click one button for success. Great. Now we open this folder and we see everything is ready. And everything is correct. And this is amazing. Absolutely gorgeous. So let's check out. Oh, we also need to update the bill of materials because now it has many more fields. Oh, we also need to update schematic then. Oh. Oh, let's do it. Let's do it. This is a very important update as well. But first, let's see that pick and place files are in order. They are stored in the archives. Very nice. And the last update we need to make is to make sure that our bill of materials is generated properly. So let's update our automatic generation settings. To add all of those into the bill of materials. Save job set. Let's rather let commit immediately, because otherwise we might as well lose something. And I don't want to lose anything. So do a quick commit. It will be an E1 updated job set boom generation setup period. Push. Code is not needed for now. We will need it in roughly 20 minutes, I would imagine, when we start implementing our brake resistor control. But for now, we need to fix one last thing. We need to go through every single component and make sure that the fields for them are no. I think no. No, I think I forgot one library. No. Let me check. I think I forgot one library. Oh, no. This is not my library. This is a generic library. Oof. Okay. Okay, then I will do it manually in the bill of materials itself. So for resistors, part number generic. We will add it to all our passive components because I don't really mind what my fab will use. It's an SMD and the manufacturer is generic, or actually any. And same here. Generic SMD, manufacturer is any. And we do it once and we benefit from it after every single iteration of the design we will have. This is setup. This is setup. We also have this with a generic part number, SMD component, and any manufacturer. Same thing here, generic, SMD, any. And 3 more components, generic, SMD, any. No. Any. And 2 more, generic, SMD, any. And here, generic, SMD, and any. Now I think we updated everything. Let's run our ERC again. It works. Make sure we push to PCB. Make sure we run ERC. Everything is correct. Save. Everything is safe. And now let's run our automation again. Generate. And let's open the folder and see if it worked. So bill of materials. Ta-da-da-da-da-da. Yes, it does work. And here it will be THT, part number. And I believe this is not a full part number. Let me actually edit manually. I will need to add connectors to my own simple library, but not today. Today we spent quite enough time. Oh, this is a part number. Okay, sure. This is a part number. And the manufacturer is this. Okay, anything else? Anything else? Nope. Looks absolutely gorgeous. Save. Was. Can you just save it? Very nice, very nice. So manufacturing files are finished in single click. They are all saved in my design way. Oh no, I forgot to update changelog. Let's actually do it again. Because we also have a changelog we need to update, of course. So let's open it in VS Code and let's go to our changelog. And in our changelog, we moved connector to the opposite side of the PCB. Rerouted SPI to not go under the IC. And also these comments are incorrect now. SDK chip select and VDD. This is correct. This is correct. This is correct. This is correct. Need to switch this. Put comma here. Period rather. Yep. Now the changelog is correct. And we can finally properly generate our manufacturing files. So let's do it. And let's make sure they are as expected. Here, outputs, third iteration. Let's open it with our Visual Studio Code. Changelog is saved, everything is saved. Now we're talking. Now we are done. And after we are done, I can push my manufacturing files to Git and be happy. So let's make one more commit. This changes, this changes, this changes as well. These are outputs. Okay. So the last commit is E1 finished. Finally, I3 of the encoder PCB for real this time. Because we already finished it yesterday once. Finish this today, another one. So let's update our stream plan. What have we already done today? Where is my checkbox? Redesign Encoder PCB for real this time. Done. Implement part number, manufacturer, and SMT fields. Done. Update all libraries for new approach. Done. Finalize job sets. Done. Oh, we've done almost everything. Ho 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 ho. And this. I don't think I need to save anything here. And let's also save our job set to our templates. Let's quickly save it to the templates toolbox, and in our KiCad toolbox, in our automations, in our templates, paste it here and rename it. This is an old one and this is a new one. It will be template KiCad job set. Very nice. And let's also commit it to Git right away. Template updated job sets. Job set template. Very nice. And one more commit. No. Oh, okay. Whatever. Looks fine. Looks nice. So now that we are done with PCB and I need to order this, and we will probably do a soldering stream in a week, 2 weeks, depending on when they arrive and depending on whether they can solder them in China or not, because I would like them to be assembled in China. It will make sure that the encoder placement is more accurate. But if it takes too much time, I rather do it at home because the boards are very simple, so we might as well just stream the soldering. Now, let's switch to the code. But before we do this, I will do a 5-minute break to keep my hand clean and to breathe some air. And in 5 minutes, we will start implementing our brake resistor. Yoo-hoo! See you in 5 minutes. Finally back. I quite literally took a walk. So let's get to coding then. But before that, we need to actually connect our brake resistor to our PCB. For that, we need to turn off the power. And I need to go and fetch the brake resistor. A moment. It is actually mounted to my test PCB when I was testing brake resistor behavior. So we need to remove it real quick. And now it needs to go here, but this looks kinda unfortunate. Kinda unfortunate. Okay, let's connect it anyways and think about the issues later. Stable enough. Oh, this is awful actually. Okay. I will need to think about how to separate them. Okay, this is attached. So what do I do about you? I can make longer cables, of course. Or I can do it like this. This works, right? Let's see if the motor have space to spin. Hello? Can you spin? Sure. Now, let's go to our design and actually see where we are connected and what we supposed to set up. Because I, of course, don't remember. Here, electronics, 2, 9 files, project. Let's see, not the PCB, but rather the schematic. Okay. And our brake resistor circuit is actually PWM brake. Let's light it up. It is attached to PA11. So let's see what was my thinking when I was selecting PA11, which timer it is attached to, pinout options, this one, and let's open this file. And let's see what I was using or planned to use. Migrate. Okay. So PA11 is where? Is here. Timer for channel 1. Sure. So timer for channel 1 then. Okay. That is our target. That is our target. So let's see if we have anything in peripheral interfaces prepared for this. Have PWM, and what does it set up? What does PWM do? Oh, so it does set up A11 and timer 4, so it's already implemented in a way. I just don't like the names. Let's rename it. Brake resistor. Let's rename this as well. Okay. Okay, all right, correct. Very nice. So let's see. Let's read this up. It would be if setup break resistor. It's a much better name. Okay. GPIO, which is 11 to a correct alternate function. Very nice. And the timer. The timer is set up. The prescaler is set to 1 for maximum accuracy. Yes. Break PWM precision, which is the same as this precision. Okay. And the frequency is the same as the driver frequency. Okay, that makes sense. Synchronizing break resistor with our FOC cycle is a correct way to do it. Okay. Sure. Okay. Channel 2. But we saw channel 1, didn't we? Actually, let's check it again, because I believe it's supposed to be channel 1. I do sincerely believe that this comment is misleading, and this implementation is as well. PA11 is channel 1. Timer for channel 1. So this should be like this, and this should be... Oof. Like that and like this. Because we are using channel 1, of course. And let's make sure that we are forcing our CCR number 4, CCR 1 to 0. That we don't have any PWM when we start up. This is important. Make sure there is no PWM after the setup. And we return from here. Why do we even have a return type? Is a quite interesting question. But whatever, I will fix it later maybe. So then PWM is set. Very nice. Break PWM set duty cycle. Okay. PWM. And this is a global function, so it should build properly without any issues whatsoever. It does. Now we need to go and implement it. To control a break resistor, we will need a PI controller. How to set up this PI controller is a big question, but we need one for sure. So let's implement it, and also implement the logic by which this PI controller will be called. So let's start with defining a PID controller structure. What will be PID? Actually, let's just copy. For now. So this is correct. I gain to define like it should be here. And pgain is too much. Let's say it will be 1, but also to do define. T will be 0 for sure, always. This is an incorrect comment, and our output and our input. So what are we outputting? We outputting PWM. So we are outputting PWM. So our minimum is 0, and our maximum is 0.0f, of course. And our maximum should be float of break PWM precision. So this will be maximum because we will use this number directly. We will put this number directly into PWM register. after conversion, of course. So also here it will be break, resistor, controller PID. Okay, and now we need a logic on how to use it. And for this, we will have to measure bus voltage. We cannot implement break resistor without knowing the bus voltage. Otherwise, we will just mess everything up. Well, technically we can. We can just turn it on every time we break, but it will consume a lot of power and will hit unnecessarily unless we call it when it's needed. So to not call it when it's not needed, let's say what? That we will enable voltage measurement. And when we enable voltage measurement, we also need to update our inverter then. Then we need to update our inverter. So, oh no, not our inverter, but rather a current controller. So current controller PID will be max min output will be equals to motor inverter, just all of this, divided by 2. And it will be minus. Then we will also have to update max controller by plus, and we also need to do the same for flux controller, because our voltage can change and we need to operate depending on the current voltage we have to work with. Otherwise, our control system will become a complete mess. So flux controller. So let's see, it should build very easily, and we will need to update this every single iteration of our control loop. So this will fly into our... Actually, where will it fly? I would imagine... should it be early or late in the call chain? I actually don't think it matters, because it will... No, but also it is not synchronized to our PWM. Right? Timers are not synchronized. So it can matter. Actually, I need to add to clarify, to check if I can synchronize timer 4 and timer 1. To do, check if it is possible to sync team 1 and team 4 PWM outputs. But before we do it, before we know it, given that we don't know it yet, we will just assume that it's whatever, and we will just use our current controller as a place to do it. And our current controller ends here. Correct? Where is it? Oh, it ends right here. Okay, that makes sense. And oh, actually, let's do it in the exact place where we update our currents, and this place is here. So this is where we measure currents. We will measure also voltage as well. Update our controllers. I would prefer max to be on top of min. And now, how do we design the controller itself? Because it's rather important. It can make or break the system, quite literally. So we do this. And what do we do then? Okay, and then we go here. 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 And we say update break resistor controller. So we will have a call to controller S32 update PI. We will only need P and I, and this will be break resistor controller, of course. And delta time will be our current controller delta time. And our current controller delta time is this. Like that. Very nicely. But we need to derive multiple things. First, we need this controller to have an error. So break resistor controller. Actually, let's update this controller only if motor inverter bus voltage B volts more than what? So we know what our average bus voltage is expected to be, and we know it because we define it here. And let's say we want this plus 8 volts. This plus and volts. I actually think I have volt left like this. Yep. Well, that looks rather nice. Let me edit everywhere. It's 12 volts. And here plus 8 volts. So if our voltage plus 8 volts, if our current voltage is bigger, then we calculate our controller. So we need to help our system to stabilize. And help how exactly? We need to calculate our error. And our error should depend on what? It should depend. Actually, maybe this controller can be a pure P controller. Or not, I'm not sure. Let's just implement it right now. So break resistor controller PID current error equals to what? We need to have a positive value that we will set to our PWM output. So our error will be this value minus this value. And this should be, of course, enclosed, or else we will not have plus properly implemented, calculated. So this value will be positive. And it's supposed to be positive so that we have positive output on the controller. But the feedback is negative feedback. And at what point it becomes negative actually? Oh no, this is correct, because this is a set point and this is a current state, and in actual error calculation for negative feedback, they would be swapped. And given that I swapped them, I just changed the sign of the error, which is what I expect. Target and value are swapped to change the sign of the error for controller to generate positive feedback. Positive output is the correct word. Now, so controller will do something, and after it does something, it should set new value to our timer 4 PWM output. So, and also a very important part that we will have else, because if this controller is not run, no matter what was the issue before, to do set team 4 PWM to 0, which we can do right away. But I think I will just need to enclose it into, actually we have a function, right? Break PMSM recycle will be 0. And I also probably want this function to be in line, right? Let's actually move it from here to here and do it static pass static force in line, like that, so that we don't have a function call here. Okay, this looks nice to me. We will also put it here, and I would imagine that it would take uint16 forced conversion of the output signal of this controller. Very nice, but we need to comment it out because I don't want to run it yet. I want to see the numbers without it. This can stay. This is safe, more than safe. And also, this is not the only thing we need to run. We will also need to reset the integrator completely. Otherwise, we can have artifacts when the voltage comes back. So let's do it. Break resistor controller PID. Current error. Let's set it to, no, it's not important because it will be recalculated with next call when it matters. What we need to do is set this to 0. To not have any set to 0. To not have artifacts after reset. To break reset. So do we need to set anything else to 0? Let me see. Max output and min output should stay the same. They do not change. And also, now looking at these values, I can confidently say that this value should be bigger. And let's say I would like to allow only 10 volts maximum on my bus. And so for me to allow only 10 volts, I should like quite literally take this value and divide it by 10 volts. And this, in this case, our error is in volts, so we will allow 10 more after we already added 8 to our target. And at 10, with this setup, we will have maximum PWM output, which is fine for me. And we can test it like this. So, to make the test safe, let's set our expected voltage to 24. And let me set my power supply voltage to 24. And what else? What else? Let's make sure it builds. It doesn't build. Happens to the best of us, of course. Implicit declaration of this bus. But this is static and force line. Oh, because I haven't included the file. Sure. Sure, the file is not included. Include our break resistor. Now we are building properly. So do we need anything else? Let me think. So our error is updated. Our controller is updated. And when we are back to 0, we just reset everything, which is proper behavior. Actually, now thinking about it, maybe we should introduce a bit of hysteresis so that we reset here not at this value, but rather at this value plus 6, so that we have a zone, safe zone, when we don't reset integrator, just in case the situation is that we are very close to this value all the time, and our brake resistor just turns on and off all the time. But let's think about it later, when it becomes an issue, or just when I have an available bandwidth in my head. For now, this should be correct. Let's make sure again that we don't have any fields we need to fill. Current error, last error, output signal, max, min, p. Okay, yes, everything looks correct. I think we can test it. And let's actually do this. And how will we do this? We will just flash it. So let's flash the proper example. And then we will change our voltage on the power supply. And we need to see if it works. I will go take my thermal camera. We will see if resistor gets hot, this one. And I also will turn on the oscilloscope, because we will probably want to poke our brake resistor components to see if they are noisy, because brake resistors are notorious for producing a lot of system noise. Especially like this one in particular, they have a huge inductance, like absolutely abysmal amounts of inductance. So we need to make sure that our system doesn't become unusably noisy. And to know where to poke, we need to open our schematic and our PCB file and make sure that we know what we would like to poke. And I would like to poke, of course, I would like to poke here to the drain and to the gate, one by one. And how do I poke the drain and the gate? To poke the drain and the gate. What the hell? Hello? Okay, nice. So drain is here, so I poke the big side to the right. Okay. And the gate is here. So I can poke this resistor. Sure. Let me go check my thermal camera. Okay, another thing we need to consider. We need to do a quick calculation to see how long can we actually sustainably push our voltage through our brake resistor, because brake resistor can become hot very fast. So my thoughts now is that we set up 24 volts as expected voltage. So the brake resistor will start working at 32. And at 32 volts, let's say I'll set up 34. And 34 volts through a 50 ohm resistor is like 0.7 amperes. So it will get hot quite fast. So how will we do this? Oh, of course, our first test will be without anything on the resistor, because we haven't even enabled the output. So let's see if the value is correct first, because our output is disabled. Of course. I commented this line out, which is a correct way to do it. So let's just add this to our live view, so that we can see if the output voltage is in the correct direction. Okay. So power supply is enabled. Oscilloscope is not needed, given that we do not output anything for now. Let's just run the code. And let's see. We have everything as reset values. Our peak gain is set up like this, which is very nice. And let me start increasing the voltage. So here we are at 31, and let's also add our bus voltage to see if it's measured correctly. So it says roughly 30, which is close enough. And let's keep increasing. 32. We should still not have a controller enabled, and now it should be enabled. Oh, now it's enabled, and the output is positive. Okay, this is very good. So we increase our PWM widths, I'd say, with voltage. So let's increase a bit more. So yes, if I increase voltage, our output increases, and given that we don't currently have an integral part, it's done proportionally. And roughly when we have 10 volts over our target, we have our maximum, which is exactly as we calculated. Very nice, very nice. So it works, and now we can go back to 24. And we can enable this line and see if I will have smoke on screen. So now let me show this. And if there will be smoke, you will be the first to see it. So let me actually increase my camera. Camera, can you focus, please? Thank you. And now, let's see if anything explodes. Let's see if something explodes. Uncommented. Set this value as expected. Move this comment to the line before. Let's test it. Let's see if I am a dumbass. And also let me remove this so that I can poke, and let me set up my oscilloscope to be ready for action. So what do I expect to see on the gate? I believe on the gate I expect to see... Actually, what do I expect to see on the gate? I'm not sure. What voltage do I expect to see on the gate? 5 volts. Okay. So let's measure the gate first and the drain later. So for this, we need to set up our attenuation to 10, because this is a probe I use. Move it lower so that we have more place to see. And 1 volt is actually the perfect setup. And timing-wise, we expect to see PWM at 20 kilohertz, which is 50 microseconds. So we would like to measure roughly 10 microseconds per division is good. So with this setup, we should see nice values. Let's set the trigger. Let's move it a bit to the side so that we can see our PWM values. Okay, this setup is finished. What else? What else? What else? To not blow up the resistor, I think I should set our... I can close this. Yes, save it. I think I should actually set the limit to a lower value. I don't need this, neither I need this. I need to go here. Let's say we expect 18 volts. If we expect 18 volts, we will have our controller triggered at 26 and the maximum will be at 36. And this way we will have our temperature risen slower. Also, just for the testing sake, let me move this down to 4. This way we will start triggering 24. The 22, I just want to make sure that I don't overheat the resistor too fast so that I can poke with my multimeter at least somewhat. And if anything will become very hot, I would have time to save the PCB. So let's flash it. So it is very flashed. And let's turn our voltage down to 18. And now if there will be smoke, you will see it first. Let's run. We are running. So our voltage measurement says 17.84. Very nice. Our controller is running as expected, right? Let's make sure it's running. Our position controller, I mean. Yes, it runs. It overshoots a bit. That's fine. Not a big deal for our current test. So now I will increase the voltage slightly. Now it's 22, measures 21.8, which is expected. And this controller still doesn't work. So now I will increase the voltage by 2 volts. So now our controller was... Why is current error negative though? What the hell? We just tested it, it worked fine. What happened? Oh, I know. It changes into 2 places. I'm a dumbass. Let's test again. This was awkward. This was a bit awkward. And we are running. Let's run. Let's make sure it calibrates first. Our voltage reading is 19.8. So we are running. Let's go back to our control system implementation. Just in case. Okay. So system is running. Also. Okay, it runs nicely. And now let me push the voltage to 24. 24. And our controller produces something. Let's see if it heats up. So, is anything it's heating? So our okay, actually cable is in the way. Our brake resistor is somewhere here, right? It is right at this connector, and it doesn't heat much, and resistor itself also doesn't seem to be hot. Let's use multimeter to measure if we have any voltage on the brake resistor output. So let's measure. Oh, we don't have any output voltage. And why I know this is because I don't have any current. Okay. And why is this the case? And why is this the case? Actually, very interesting. We don't have any current flowing. Let's open STM32 G4 E1 datasheet. And let's see if PA11 is actually... Oh, I know. I know. I'm such a stupid person. Fuck me. I didn't even set up the PWM output, of course. Beef setup brake resistor. Now it should work. Let's go again. Like we haven't had this line. Let's make sure it calibrates first. I will still prepare multimeter because we will need it. thermal camera is ready. So our example runs. We measure 19 volts. Let's go higher. 24. Yes, current is flowing. Something is happening. Something is getting hot. So let's see. So this is our brake circuit. Something is warming up for sure. Brake resistor is cool for now. So something is warming, but not very hot. Let's measure the voltage. Let's measure the voltage. Let's measure the voltage. Okay, where will be plus, where will be minus? Let me see the schematic, not actually PCB file rather. The plus will be on top and the minus will be on the bottom. Okay. So this is the minus then, and this is the plus. And our reading is 3 volts. Was? Oh, it is correct, because we output only very small PWM. So it averages to 3 volts. Sure, that makes sense. Let's see if temperature increased. Oh, our brake resistor is kinda hot already. Okay, very nice to know. It's 50 degrees, it's not hot, it's still touchable, but it's just getting there. And our circuit is fine. And this is our brake resistor after like roughly a minute with only 24 volts and only like 4 of them visible. So the brake resistor is not a huge help. It will overheat very fast actually. Now let's poke around with our oscilloscope. I will now touch my probe to the gate of the brake transistor. And let's see what we see. So this is our gate of the brake transistor. It looks very clean actually. Oh, I almost broke everything up. Let's make it closer. Closer to the edge. Let me touch it again. Okay, and let me, actually I would like to see it even closer. To here. Let me touch it again. Very nice, and let me stop it so that we can analyze. And I also will lower the voltage down to not overheat the resistor, because the temperature right now of the resistor is 70 degrees. Holy cow. This is a very hot resistor already. So this resistor is this resistor underperforms my expectations quite a bit. It's 75 degrees already. But for now, for now we need to analyze our measurements. Let me remove my multimeter rather, so that I can have access to the oscilloscope. Done. So let's see. So we have almost perfect 5 volts, which is expected. Let's move our line and let's get closer. The line is clean. There is no noise on it. It's very, very nice. And this is as expected as effect of transistor opening, this bump. So nothing on the start. And how our end looks. Very nice as well. So our brake transistor gate looks clean. And now we will need to measure our brake transistor drain. This is the most noise inducing part. So to measure drain, we expect there to be what? we expect there to be 24 volts roughly. So what we need to set up is actually 5 volts per division. Yes, 5 volts per division will show it nicely. The same timing, and trigger should be higher. Trigger should be roughly at 15 volts. Okay, so let me enable the voltage, higher voltage again to 24. We at 24, and now I will touch our drain of the transistor. So let's see what do we have on our drain. Okay. Oh. Okay. This is no, it is expected because drain is connected to up. Yes, expected. So now let me select what we will measure. Is this good enough? Nope. Actually, let's analyze this one by one. It's very uncomfortable to do it in my position, in my body position. So let's stop. Let's lower the voltage. And let's see what we see. So we have a bump in voltage, which is fine. It doesn't seem to be noisy at all. It's just a voltage bump. So we don't have any like terrible ring or something. Also, let me check the PCB temperatures. PCB temperatures are fine. Nothing on the PCB is hot. The only hot thing is me and the brake resistor. Okay, so let's turn on our cursors. Let's see, so this is roughly 25, 23, 24, and this is roughly 1.5 volts higher. So this is not critical at all. This is not critical at all, and so the end looks clean as well. Let's do what? I would like to enable higher output of the brake resistor, but I'm scared that I will just explode my brake resistor, like quite literally. Which is unfortunate because even on such a low voltage, it already overheat very fast. I just don't have the resistor to take so much amps. Oh, actually, I have a DC load. I have this device here, this beauty. So I can connect a high load. And I can set it up to work in a resistor mode. So let's do this. Why wouldn't we, right? Why wouldn't we do this? We wouldn't do this because it is not connected to power. One moment. Oh. Okay, this is connected. Turn it on. Let's make sure that these are tightened properly. Let's remove our power and disconnect this overheating thing. for the testing purposes, of course, the most important part is that we saw that with this resistor connected, we don't have noise. And this is the most important part. So the brick resistor circuit is not a noise producer, which makes me happy. And now we just need to make sure that we don't have a circuit overheating and circuit producing noise itself on a high load. And for high loads, we need something that can take more than this resistor, which is a DC load I am setting up. So let's remove this and test everything properly as if we are professional engineers, which we kinda are, but not really. Okay. It's kinda hot. Remove. Let me attach my DC load inputs, so I will need to move stuff around. Okay, my table will suffer the consequences of my decisions. So I need to move it even closer. And I think I will need to set it up like this. Good enough for us. Please stop. Please focus. Camera. Okay. So let's order touch. As we saw, our power is on top. So power is on top. Don't have much space here. Where is my screwdriver? Okay. First probe is attached. Is it rigid enough? It is. The second cable wire. We should first unscrew it. And let's connect. Is it in? On the camera it seems like it is. Okay. So let me screw it in. Okay, let's see if it's rigid enough. It is. Okay. So now we have our DC load attached. And we can simulate our DC load as our resistor. So let's set it up. Let's first of all turn on the power. And it says 0 because 0 is connected to it right now. Constant current, no. What we need in the mode is a resistor mode. And how do I set up the resistor mode actually? It's a very interesting question. Current. Constant current. Oh, this is a resistor mode, right? Yes. Yes. So let's set it as 50 ohms, and voltage range 36 is fine, and current range 30 is fine. So can you see it? I think it's not really focused on the correct place. Actually, let me just do this. So now let's see. I will increase the voltage on our power supply to 22, and it should be absolutely fine. And now I will increase it to 24, and we see 24 on our, oh, I forgot to enable it. So now we see that we have roughly 400 milliamps, roughly 9.4 watts flowing through our load. So with me increasing voltage, it will be increasing, correct? It increases slightly which is expected. And at 32 volts, we just see the full voltage, right? Yes, exactly. We just see the full voltage all the time. So it seems to work correctly. Let me see our debug view to make sure that we are showing correct values. Are we even in the debug view? We are not. So let me lower the voltage to stable 20. And let me go to the debug view again. Let's run it. Let's wait for motor to calibrate itself. Of course. And now after we test it again with our debugger enabled, we will start probing with oscilloscope. So let's see, motor is fully calibrated. We don't see anything because we're at 20 volts. I'm increasing the voltage to 24. We see that we produce roughly 20% of our... No, it's less than 20%. It's notably less. Yes, because error is only 1.5 because current flows to the load. Okay, let me increase the voltage. Our values are increasing, so we increase the current essentially and effectively. Okay, at this point we are maxed out. Okay, let's put us to half and start probing with oscilloscope. So we are at half roughly here. Good enough. So let's switch to our oscilloscope. Now we have all the time in the world to measure it without the rush, given that we are not using external resistor. So let's start the measurement and let me poke the drain pin. Hello. Drain pin. Hello. Will you measure this? Something? Anything? Okay, my board is in a very awkward position. So, rather, show me anything. Actually, anything. Not like this. What? Okay, am I even poking the right place? Let me see. No, I'm not confident that I'm poking the correct place. But I do. Oh, I can just poke the output. Very nice. This will be also drain. What is that? Why do we see this? Have we enabled an AC mode? No, we're in DC mode. What is that? Okay, this is interesting. First of all, we have some sort of spike, which is relatively small. But what is going on? Let me poke the gate. This is gate. Gate looks clean. Oh, wait, hold on a second. What do I need to measure? Hold on a second. What should I even measure? Do I even measure correct thing? So what do I need to see here? Yes, I will see almost 0 here because like there is no load. So what have I expected? I should measure the brake resistor itself, which is attached from V-bus here. So I'm actually measuring V-bus. Oh, but no. Drain is kind of important because we saw some noise there. And actually, behavior is different from when we had our transistor attached. Not transistor, but resistor attached. We will need to remeasure it with resistor for sure, but let's, for now, switch to increased voltage. 5 volts, and let's me poke the output. And the output is stable. Wait, but I would like to see the PWM. Oh, what is going on? Hold on a second. Let me measure the voltage. I'm kind of confused right now. I am a bit confused. Oh. Confused I am. So let's see. Our voltage on the output currently is roughly 50% PWM is what? 26, and we have it's 26 and jump. No, it's just 26. So why does it measuring as if the voltage is just constant there? I need to measure between ground and what? Oh, this is very confusing. Oh, very confusing indeed. So what should I measure exactly? What do I want to see? If I measure pin 1 on the connector, I just see the voltage on the bus, which is constant. Maybe I should actually measure voltage after the resistor, which is on pin 2, which is connected to ground. But this is exactly what we measure, with a little spike. Little spike and little growth. Yes? Hold on a second. Is this how it's supposed to work? I'm confused. So let's analyze. We see some ringing, then increase in voltage. And increase in voltage means what? And also this increase in voltage happens only roughly half of the period, which is exactly correct given that we are only providing half of the period currently as PWM. The ringing is annoying. It is unpleasant and it shouldn't be there. This ringing is annoying. But the very big but is why the next line is straight. If it is inductance, it should look curved. So what this line means is the increase in voltage on the resistor over time, which means that resistor is highly inductive and the voltage doesn't change immediately. But why is it linear? is it so much inductive that it just doesn't have enough time to do anything. But when we turn it off, the voltage drops immediately, which is not how it's supposed to work then. Let me save this as a picture for analysis later. Save image, removable disk, folder 0, save. And let's also save another picture, closer and higher, closer and higher. Because the voltage seems to go negative completely, which is awkward, no? I am confused. Pretty much. So, storage, save image, removable disk, folder, save. Now let's see if the ring will go worse or better with our increase in our period. So let's run it. Let me touch it. And let me change the voltage to a higher value. So yes, with voltage increase, this spike increases as well. Until it doesn't. And it doesn't increase when I turn off. Not turn off, but when the PWM period is maximum. So when our PWM period is maximum. And let me decrease the voltage. So with decrease, it just drops until... Oh, what the... What? And there is some kind of crap when we are at very low... PWMs. What is this? I'm so confused. Let me see if my board is overheating actually. I will save this image to the storage as well. Yeah, save. Let me wait for my camera to turn on and let me push maximum PWM through this. So increase the voltage to 32. Let's see if anything overheats. Let's give it a moment. A moment of your time. PCB. No, any circuits around the brake resistor don't seem to be hearing at all. So circuits are cool as a cucumber, but everything else is not. Not everything else, but the brake resistor behavior is completely awkward. But we wanted to test overheating. We did. Circuit doesn't overheat. Brake resistor overheats very fast. And let's disable our DC load. Let's remove it from the connector and let's connect our actual resistor back and remeasure with oscilloscope to see what the hell is going on. What is going on? Let's turn off the power, but first let's make it lower. Turn it off. Where is my screwdriver? It's here. So nothing here is warm. Motor is cool. Okay. So let's move ourselves back. And let's connect back our moment, hiding cables, wires. And let's connect back our resistor, which is already cooled. So power is off, screwdriver is on. Installation is in progress. Okay, this is rigid enough. And let's put second connection point. So it is rigid enough as well. Let's move it from the shaft. Enable power supply. Let it calibrate. So it did calibrate, so now it should start spinning, which it does. Let's increase the voltage to 24 and see what we measure here. So we are in a running mode. We have 5 volts per division. Let's move ourselves over. No, actually, let's not move ourselves over. Let's be as we are. Trigger as well. So I'm touching the actual drain of the transistor, which shows 5 voltage. Wow. What? The behavior with DC load is different for whatever reason. Okay. Let me increase the voltage, and now it works. Maybe DC load had some kind of odd behavior and it just didn't work correctly, but with proper resistor it works correctly. Okay, I increased the current very quickly, as you can see. I just didn't want my correct resistor to overheat, and I wanted to see the edges, and to do it again, let's move our edges here. And we will repeat it one more time. So increasing the voltage until it can't any longer. Hold on a second. No, go back. Why is this the case? Because we were supposed to have at some point we were supposed to have a flat there, but we haven't had a flat. Now let's actually change the scale to see the whole picture and do it again. Increasing the voltage. Okay, 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 okay. Sure. Oh, what? Oh, I know. And the reason is my power supply. Oh, is my current limit on the power supply. Well, let's test this again, but let's make sure that the resistor is not overheated. Yes, it works nicely. I already see that it works nicely and without noise, and I think DC load has some internal circuit that wasn't exactly as resistor, and this is why we saw completely different behavior from what we expected, because we were not measuring actual resistor. we were measuring like a very active circuit with transistors and stuff. So it was not a correct test. Our resistor is at 65. I would imagine that after this test right now, it will be at 100. So let's do it very quickly to confirm and be ready for the smell of plastic. And I say to myself, you of course will not be able to see, hear, smell anything, but I will probably smell some burned stuff here. So my current limit is set to the maximum. I'm touching the oscilloscope. Let me move my measurement to 5 volts minus 15. Very nice. Now let me actually remove our cursors and let's do the test one more time. So we are at 23, 24, 25, 26, 27, 28, 29, 20, 30, 32, 34. Yes, exactly. Very good, very nice. Ringing is minimal. And let's see how hot is my resistor rather. So everything works. We haven't seen any like terrible noise, but we will also need to try this with, how do we measure noise if we have any actually? I'm waiting for my thermal camera to set up and our resistor is, oh, it's only 78 degrees. I did it quite fast. It didn't have enough time to overheat. So now we measured that our resistor is overheating rather fast, but our circuit works pretty fine. We measured, how do we measure noise if we have any noise? I think we have to subtract mathematically, because if we use our AC mode will show a huge spike. Let's try. Like nothing stopped us from trying, but I'm sure that it will not work. Almost sure. Let's sure AC mode and let's do the same test. I'm touching the drain of the transistor and I am enabling and increasing voltage. 23, 24, 25, 26, 27. Yes, and it's awkward as hell. And we are, yes, AC mode didn't help us at all. So what should we do then? How can we measure the noise if we have any? How can we do this? Actually not sure if this is such a big deal, because we clearly see that there is no ring, like nothing rings. So we don't have any high frequency components, which is exactly what is problematic with noise. So my circuit works and it works fine and the resistor works fine. So, and also it works absolutely fine without I. So it's just a pure P controller, which is more than fine for me. I'm absolutely fine with that. So should I do something or shouldn't I? Actually, I think I shouldn't. I think it was enough of a demonstration. So let's actually think about the implementation details now. What implementation details should we think about? Let's see. First, we need to specify, definitely define will be device, break, voltage, offset. Let's say it will be 8 volts compared to whatever the current default bus is. And also let's define device max break voltage error. Let's define it as 10 volts. So if we have 10 volts, we would like to see our whole period on the resistors so that the power supply is just connected directly. And I need to add V here as we measure this in volts, of course. And let's add it to the code. Let's add it to the code. First, we will need to measure here. Instead of 4, we add this. This is a terrible name, actually. I actually don't like this name a lot. To think about better names for these definitions. Okay. But they are functional, and when they be renamed, they will be renamed properly. Our brake resistor runs at this frequency of our current controller. We also need to think how to synchronize them, but it will be later, of course. And what else? What else? Oh, we also need to update our controller. I don't think I will use any I for now, even though I will run PI as our controller. I will have 0 in the I gain for now, because for me, it seems like it works more than fine with 0. And I believe that it can be a purely proportional regulator, but I'm not sure. I'm not entirely sure yet. I will read up on it. And now I want to measure if we have any problems with performance due to this controller being implemented. No, our performance is almost identical as it was before, which is expected, of course. It's maybe like a few dozen cycles longer, which is to be expected. And here, instead of 10, we will put our second definition, which is this one. Our second definition. And let's assume that this is exactly how we want to set it up for now. I kind of like this approach. So I would say that we can consider our brake resistor circuit and brake resistor control to be implemented. Hooray. So now, the question to the chat is whether I should continue and do another part of the code or whether I should stop today. If anyone wants to vote or say something, if not, I'd say I finish for today. At least on stream, I will probably work off stream for a few hours longer. Okay, so then it's all for today. Thanks anyone for watching, who watched. If you are not following yet but would like to see more, please follow. I would appreciate it a lot. And I'll see you in the next one. Thank you for watching. I hope you enjoyed it, Multiplexer 8. If you enjoyed it, please follow. I would be very thankful. And if you have questions, please feel free to ask. I'm still here. So I am available if you want to know anything. Already followed. But I don't think you are following me. Don't lie to me. Thank you for watching. Okay, see you next time. Bye bye.